We are ready to start. Okay, thank you, Alison. And I would like to welcome you all to the SmartSat CRC Distinguished Speaker Series. Today is our guest is my Professor Marco Martorella from University of Pisa, and this is represent our 70th distinguished speakers. So in doing so, we acknowledge the traditional custodian of the lands and water across Australia, where we conduct our business and pay our respects to the elders past and present. SmartSat CRC is committed to the health, safety, and welfare of our staff, our partners, students, stakeholders, and the broader environment. We are passionate about creating an inclusive workplace that promote and value diversity, excellence, innovation, collaboration, and integrity. And we strive to constantly demonstrate this value through our behaviors. We are committed to conducting ourselves with the courtesy and the respect at all time. It really is my pleasure to have Marco here. And tonight he will talk about the space-related research activity at the radar and the surveillance system in the National Laboratory. This laboratory is already 10 years and he's a lead of this lab with 40 people employed, they are staff. And that is, of course, mainly are researchers and engineering. Today, we talk about some research activity in this laboratory, the radar and the surveillance system national laboratory, and he will present some microsatellite SAR clusters for EO and military application, and also some experience with the stratospheric balloon-borne uses SAR and space situational awareness. That means by radar system. So welcome to Marco. Marco is received the laureate degree, bachelor plus master in telecommunication engineering in 1999, and in 2003 the PhD at University of Pisa. Is an author of more than 250 international journal and conference paper, 3 books and 19 books chapter. He is a member of IEEE IS radar system panel and many members at NATO panels. So let me really welcome Marco. I know him personally is probably more than 10 years, and always have you is really a pleasure here in Adelaide. Marcos, the floor is yours.
Thanks, Nicola. Thank you very much, and thank you all for being present here in person and online. I can't see the online people in face, but thank you very much for being here. It's a pleasure for me. The first time I came to Adelaide was in 2001. I was actually doing part of my PhD at Melbourne Uni, and I came across and I met fantastic people that have been collaborating since. I would say, some actually retired, but most of them are still working at DST, University of Adelaide. And in the years, I've spent quite a lot of time in Australia for different reasons, research, but also because I'm married to an Australian girl, so we had to come back every now and then to pay a visit to the in-laws and the relatives, and it's always a pleasure for me. As Nicola was saying, our lab has now a bit of history, and I would like to talk to you about this lab a little bit in general at the beginning, and then I will talk specifically about all the research activities that we are doing in the space domain, which is probably what most interests you as it's a SmartSat. So I hope you'll find the interest in what I will be telling you today. My main goal here is to let myself known to you and hopefully do collaboration with some of you in the future. Okay, so I will start with a bit of history. As we say, we started in 4 people about 12 years ago. It's a little bit more than 10 years now. And the person that you see at the top of the pyramid is Professor Dallamese. Now is retired, but he's the founder of this national laboratory. So he shared his vision with us, so we decided to embark in this adventure, and we created this lab. It was a bit of a gamble at the beginning, but it proved actually to be a winner. And so that dates back in December 2010 when we started. So what's the mission of this lab? We place ourselves in that section that some describe as the valley of death. It's in between basic research and the industry. So we target TRL typically from 3 to 6. That's our main goal. But that doesn't mean we don't do basic research, so we do. And I will show you in some more that we progress beyond TRL 6 in our joint ventures with 2 spin-off that we created and other industry that we collaborate with. So just to give you a bit of information about our structure, it's very simple. We have a director, it's me in this case, and we have a steering committee. We do the managing, the strategic thinking, and then we have what we call the established research areas, which are pillars where we substantially carry out our projects. We get funded, where that's where our expertise mainly lie, and the work where we are known the most. And then we have exploratory research areas that we often self-fund internally with internal funding, and then we believe it's going to be a source of funding for the near future. Okay, one thing that I want to tell you about this, we are 100% funded with project money. There's not a single penny that comes from the government or from any stakeholder, so we had to earn our living every day by bidding, competitive bids, and winning grants here and there, collaborating with the industry. I will show you a little bit of this, how we operate. So we started with 4 people, and in 10 years, roughly, we grew up quite nicely, up to 40 people now. That's a breakdown of our sort of categories and how many units per category. So we got 17 employees. Those are permanent staff that work with us. Then we have consultants, about 16. I am a consultant because I actually work for the University of Pisa, but I act as a consultant for the lab. So there are other professors who act as a consultant within the lab. And then we usually have a number of scholarships that we fund, and this is in collaboration with the University of Pisa. So we've been growing steadily since we started. In 2021, for example, we created a new permanent position and 2 new temporary positions. Considering that we get someone who leaves after some time for different reasons, let's say that we grow at the moment. So 1 or 2 person per year. So we found a nice equilibrium at the moment, which of course depends on the environment, the amount of funding we receive, and so on and so forth. So it's a delicate equilibrium, but I think we've found it roughly. So since 2015, we work within the boundaries of this quality certification, which is the ISO 9001. It's important to us because this certification allows us to have certain contracts from the various ministries in Italy, so government funding, and also some large industry require this certification. So it's a quality certification, so we have to work in a certain manner. No more about that. I'll talk to you about this. So we have a joint lab together with the Italian Navy. This is very important to us for 2 reasons. One is because it gives us a direct link to our MOD, which is probably funding nowadays about 70% of our projects. And the other thing is that this lab is located within the Italian Navy base in Livorno, which is not far from us. And they have huge facilities for testing RF systems such as radars. Okay, so they have anechoic chambers, they have test ranges, indoor, outdoor, and then the ability also to install radar along quite long stretch of coast and look at maritime targets and so on and so forth. So we held a couple of very important trials there, one for the European Defence Agency and one for NATO, where some like 10 radars were deployed by as many nations. So it was these two particular trials were for the largest we held within this joint lab. We spun off two companies. The first one is a radar producing company. It's called ECOS. It exists since 2015. It's not a spin-off anymore. Like now it's a full-on company that is completely independent. I mean, when I say independent, it's financially independent, but of course it's very much tied to us, as I will show you in a couple of slides. The other company is about producing antennas, developing RF components and so on and so forth. So it's quite orthogonal to the first one. And actually we find the two combined together being very, very useful to us to develop new systems. In terms of expertise, we got sort of our main core business is radar, of course, and radar imaging, remote sensing from satellite, for example, classification, development of radar systems, analysis of radar systems. Then we have, in the space domain, also we have a quite good branch that does space situational awareness, and then we have got all the EM stuff, metamaterials, antennas, electromagnetic propagation, so on and so forth. So one important slide I want to show you is this one. So we have created, in our little ecosystems, we have created what we call an innovation cycle. The concept is very straightforward. So let's start with basic research. Basic research is, of course, the fundamental innovation step that you have to undertake to come out with something that can be a breakthrough, can be a disruptive technology in the future, okay? But we need also applied research. Applied research is when you take some of those ideas, blue sky ideas, and you try to apply it to something, and you start channeling that effort into something that's going to become some technology, eventually some capability that is going to be applicable by someone, some users, okay? And this is done usually through a technological transfer, and that's where, you know, it is important that you have the right ecosystem that is not just the university, is not just the industry, but there has to be a synergy, okay? And that when, you know, the idea is good, when everything, all the pieces of the puzzle get together, you finally get to innovative products that get into the market and get sold. We implement this. The three elements that we have in place is the university, of course, the national lab, which radar and surveillance systems in our case, and the two spin-off companies. It's a small ecosystem, but it's actually very functional. And you can see how this is a loop that feeds back to the basic research. You know, basic research can be done blue sky without thinking. Today I wake up, I read a paper, ah, so interesting, I do research. Well, it can be lucky that that piece of research is going to be creating then, you know, the momentum and this cycle, you know. But it is much better when you have an idea of where the market is going, what the needs are, because you can channel your basic research into something that more likely is going to be successful. So there is benefit into that. Not least also what you go and take back to university in terms of teaching, in terms of attracting students, so on and so forth, which become a feed also for this, okay, from the human resource, you know, potential and generating knowledge that adapts to what you are creating. Just one example of success story. I brought this one because it involves Australia, right? So we started in 2010 doing research in multi-channel radar imaging, right? At that time it was something new, something attractive. We started with developing a multi-channel radar imaging demonstrator, is the one that you see in the picture there. The core of the demonstrator, so the hardware and the software that we created within that demonstrator then serve the purpose of creating some different stuff, which is a ground-based SAR prototype. Which is a ground-based SAR prototype? It's a radar that goes on a rail on the ground and is able to form SAR images, which is our high resolution radar images of whatever you get in front. This is for, you know, relatively short range. but you can monitor, with this type of radar, you can monitor infrastructures like bridges, dams, buildings, landslides, open pit mines, and so on and so forth, avalanches. There's a number of applications here. We had a first contract from CSIRO to produce this prototype. Then we developed additional sort of technology around that. CSIRO bought 3 of these radars, okay, and now it's become a product of the company, selling really well. Not only, but it's become also one of the main services the company is providing together with other geologist-based companies. So that's just one of the examples of this innovation cycle. And of course, this fed back is now that technology is going into inspiring new basic research to attract then more funding for development later. Well, this is just what I call this, small ecosystem. Of course, it's scalable, right? It is scalable, but what I wanted to stress here is that, we are not tied to that model only. We do a lot of collaboration, external collaboration, and this is very important. And one of the things that I have highlighted here is international research projects through, for example, bilateral, multilateral government-to-government agreement. I mentioned this because years ago we did started in a government agreement between Italy and Australia. This thing is being rehearsed, and it's one of the things I'm working on while I'm traveling around Australia to try and produce a portfolio of possible projects that can go under this bilateral agreement. We do a lot of work within the NATO, within the European Defence Agency. One of the projects I will be talking about today, Miracle 2, is microsatellite SAR clusters within that. We are very active within the IEEE. This is to say that the breadth of our network is very wide. When we're talking about NATO, EDA, and IEEE together, we're covering pretty much the whole world, and all the major industrial players and academic players and research and technology organization players. Just to give you a little bit of a visual map of this, we do collaboration with a lot of countries, and a lot of universities, of course, a lot of high-level research institutes, like Fraunhofer, Honora, DSTG, DSTL, Air Force Research Lab in the US, Naval Research Lab, and so on and so forth. I'm talking about large institutions, and a large variety of industrial partners, of course. We do work also on the consulting side, so we don't just do research projects. We act also as problem solvers, and we often develop parts of systems for companies and so on and so forth, which of course sustains us from that angle as well. We have to sort of create a quite wide range of opportunities, sources of funding, because as you know, if someone closes the tap one day, you still have other taps that can contribute to your funding for funding research. A couple of numbers that might be interesting to see. Number of projects, as you can see, there's a slight increase in the years. Last year, 2021, we reached 35 active projects. The yearly budget is on average just above 2 million per year, 2 million euros per year, which is enough for us to go on and have enough to pay for all the human resources and carry out all our projects. Here is like a bit of topics that are quite hot at the moment, and as you can see, space, there are 5. The number is the number of projects that are actually active in that domain. So space, at the moment, we have 5 active projects. So it's a big component in what we do in our lab. So just to mention a few achievements in the last 10 years, we grew by a factor 10 in 10 years, which is not bad. We have employed roughly 20 researchers in the years. Some have gone. At the moment, we have 17 in our lab. We provide an average of 3 to 4 scholarships, research grants per year, and we pay that to University of Pisa to have PhD scholarships enabled or postdoc grants as well. We can say broadly that we have become the reference point nationally and internationally relative to radar. I mean, we are called by big industry across Europe to participate in European projects because of our expertise in both radar and electromagnetics and surveillance systems. We have attracted about actually more than 20 million euros in research fund in the last 10 years since the beginning. Of course, at the beginning it was little amount, and then as we grew in numbers, of course, we grew also in the amount of money that we can generate yearly. The last point is very important to us. Despite the hard times that we've gone through in these years, I can say that we have shown a lot of resilience. You know, we haven't really been impacted dramatically, which is very important to us. It's important to the people we employ. A lot of young researchers who see us as a well-established research laboratory, which is important. Okay. In terms of strategy, these are just general things. I think I'm going to skip that, but it's one thing I want to say is that we, as I said at the beginning, we place ourselves in the value of death. We really try to stay within that interval TRL between 3 and 6 because we see that as is probably where we can be more effective. Okay, and we want to do this more and more in the following years. There's another thing. In Italy, we don't have a DSTG or DSTL. In Italy, such a structure doesn't exist. So the MOD funds directly the industry, the academia, and so on and so forth. So one of our goals is to become a reliable substitute of these large research centers for what concerns RF. And I think we are getting there slowly, but that's one of our goals. And it's an important achievement for us because it will give us, I think, in the years, more resilience and more stability, although we would be more inclined to do military research, but this is happening already now. You know, when you do radar, I mean, there's so much you can do for the civil applications, but it's a lot more that you can do for the radar, so that's inevitable. We produce an annual report every year since 2019, and the 2021 has been out for a few months now, and if you're interested, you can have a look at that. There's many more details than what I presented today. There's many more details about all the projects that we have active at the moment. Few more numbers that you might be interested in looking at. Okay, so this concludes the first part of my presentation. I'm presenting my lab. Now I will go into the space domain. So what we've been doing in the space domain, what we are doing in the space domain, possibly what we can be doing in the near future. So I will be talking about these microsatellite SAR clusters. I will talk to you about how we have been involved and what we have produced in terms of tools for improving and analyzing SAR images. Okay. And a third point is, which is quasi-space, it's not real space, let's call it D-space, a project on the Stratospheric Balloon-borne SAR, which is for us, since we haven't put any payload in orbit yet, it's a step to get to space. The last thing, which is, that was looking down, now we're looking up. We are currently involved with a lot of space situational awareness with our systems, and I will show you what we're doing in that domain as well. So let me start with the microsatellite SAR cluster. So the reference project I'm talking about is called Miracle 2. I mentioned it before as one of our sort of collaborative projects. The funding institution is the European Defence Agency. Actually, the project's finished. This is an initial duration, but then because of COVID, it was extended a little bit longer. So we've actually finished in 2021. This was a collaborative effort between Italy and Norway, and it involved Kongsberg Space. You're probably familiar with that company. It's pretty big in Norway. FFI, which is the equivalent of DSTG in Norway. And then it was us and University La Sapienza in Rome. So this project looked at imagining having, instead of a single bulky powerful satellite SAR, looking at how we can replace that with a cluster or a swarm of much smaller satellites. So what would the benefit of that be? Will we get performance losses, performance gain? What can we enable that is not available when you have a single satellite? Okay. So we looked at that, and we looked at the resilience, scalability, flexibility, and particularly a couple of things that we took care, which is imaging quality improvement compared to the single satellite and new available SAR modes. So I will talk about these things specifically today. I wouldn't touch the mathematics behind it, but just show you some preliminary results and things like that. So for what concerns image quality enhancement, we'll be looking at resolution and focus enhancement and real multi-look Despeckle. So these are two important aspects when you do SAR imaging. So resolution gives you the ability of seeing fine details. Focus enhancement gives you the ability of getting sharp images, and then can be used effectively, for example, for recognizing targets. Okay, let's not forget this was a military-funded project, so we're mainly interested in looking at targets. And then the real multi-look Despeckle. Despeckle is something that we apply to SAR images to remove a noise effect. It's called speckle, which gives SAR images that funny look of salt and pepper type of images that create this noisy image, and it's disturbing somehow and hiding possibly some features that you want to be highlighted. So what happens with the resolution and focus enhancement? So what we want to do is to get high resolution. Okay, so to get high resolution, you need to have long apertures. So the longer the aperture, and for synthetic aperture radar, the aperture is the sort of a piece of the orbit, the length of the orbit that you're using, and where you're coherently integrating all the signals that you receive from every single point across this arch. And you can, of course, in theory, create very, very long apertures. The problem is that it takes time to form this. I mean, the satellites, they fly pretty fast, but to create an aperture that gives you a fine resolution, you still have to wait a few seconds. And within those few seconds, what happens is that targets move. Not only targets you're interested in, even trees, even certain vibrating objects, they appear defocused in your image, and it's not, I mean, there are ways of focusing that better, but there's still a limit, a physical limit that you can't break, okay? So it would be interesting to see, well, can we form an image with that resolution with a shorter time? And that's what you can do, for example, with a cluster of satellites rather than a single one, okay? Just to give you a couple of examples here, I mean, this is just simulation, but it is not, my wife's trying to call me now. Can't do it. So what happens is, first thing we did, okay, let's see how we can do that. So basically, imagine a simple configuration when you have 3 satellites on the same orbit, okay? So one satellite forms a bit of the aperture, the other one forms the other bit, and the third one following. Yeah, so you basically have 3 satellites that at the same time form the same, let's say an arch that is the sum of the 3 bits. Okay, so they're on exactly on the same orbit, so you can imagine this can be done. So this allows you to form, or coherently use all these signals to form an image, the same as if it was a single satellite that actually crossed all that orbit. But you do it if you have, for example, 3 of these systems, you have now shortened your coherent integration time by 3. If you have 5, you would reduce it by 5, and so on and so forth. Of course, there's a trade-off at some point between benefits and cost, right? But anyway, that's the underlying concept. So what we did, we simulated a scenario where you have, some points on the ground that are scattering back energy. This is a sort of point-like model, and then you have a point that actually is vibrating. Okay. It's oscillating or is changing its position during that time, which could be anything. It could be a target that is moving, could be a tree that is oscillating, it can be anything that moves in the image in that period of time, which is, again, a few seconds. And what happens is that if you try and form an image with a single long CPI SAR, then you get this target gets blurred. You don't see a sharp image of that single point. Whereas if you can form this image using a cluster of satellites in that formation, then you can get a well focus. Okay, and that's an example of resolution and focus enhancement. The other thing is the multi-look despeckle. So the current method for despeckling SAR images, there's a few of them, but they all trade off despeckling ability, so the ability to reduce the noise, the salt and pepper noise, and on the other end, there's a loss in resolution. So the more you want to despeckle, the worse is going to be your resolution. So losing resolution means losing details. Okay. I'm not going to go into the fine details, but if you use the same combination, satellites that are on the same orbit, just offset in time, then what you can do, you can form what you call a real despeckle. And a real aperture despeckle means that now you are able to remove with the same effectiveness the salt and pepper noise without any loss of resolution. And that's only viable with this. So this is just a couple of examples, okay, of what is already available with the current systems, but that we can do better. Let's have a look at other modes now that can be enabled that are not available for the single SAR satellite. First, simultaneous across-track and along-track interferometry. What is this? I mean, for those of you who are not very familiar with these terms, interferometry is very important, for example, to measure ocean currents, for example, if you look at Earth observation. It's very important for detecting moving targets and that are embedded into a strong cluster. So you get, for example, an important vehicle on the ground that is masked in between static objects like buildings or other strong reflectors. The target is moving. Well, with this along-track interferometry, for example, you can remove all the static clutter and bring up the target that you want to detect. At the same time, you can do cross-track. Cross-track serves the purpose, for example, of measuring heights of objects. So that's also important in the civil case to, for example, form three-dimensional topographic maps of the Earth. Okay, that's what is done currently. And with a formation of 4 satellites, even 3 satellites would be enough. You can actually implement both at the same time. So it is not just a matter of doing 2 things at the same time, but you can actually enable the ability, for example, to measure, to form a 3-dimensional image of an object that is moving. So it's a combination of the 2, is more than the sum of the 2. And the last thing that we can do is 3D imaging. Okay, one of the things that we have implemented on the ground is the ability to form 3-dimensional imaging of moving targets. This is an example here. So what we form is a composition of point targets similar to 3D laser scanning, to imagine to create 3-dimensional images of objects. And we can bring this up in space. At the moment, we are able to do it on the ground, in the air, and that's the idea to do it also from space, which will give us the ability to form 3-dimensional images of objects on the Earth, which helps greatly the ability to recognize objects. Okay. Again, very important from the military perspective. We have developed a lot of, I was saying at the beginning, tools to actually improve and analyze SAR images, improving in a sense of being able to present a product that is more understandable by a human operator. And in terms of analysis, the ability, for example, to automatically detect targets, to measure some parameters of this target. That can be geometrical parameters, can be behavioral parameters. And so we encapsulated in this it's a suite of tools being encapsulated into a graphical user interface. It's a point and click. So this is completely usable by a non-expert, someone who doesn't understand how a SAR image is formed or what to do to detect targets, just want to do the job. So it's fully automated. We have a full automated mode, and we have a semi-automatic mode where a more expert user can actually tweak a few parameters to get things even more effectively. Just to give you an example, we have Despeckling in it. You can see the classic salt and pepper image on the left. Okay, you can see it looks like noise, right? That's disturbing. It may mask some targets, some features. The image on the right is a despeckled image. Okay, we have the ability to separate land and sea. So we can, for example, by doing this, we can neglect what's happening on land and just look at sea, for example. So more effectively, when you go and search for targets, you don't have to search for the entire image. We have an automatic target detection. So all the targets in the image are automatically detected. And then we have a labeling system and a target extraction system that then takes us to the next step, where we go through feature extractions for each of these targets in terms of size, in terms of the fact that they're moving and cruising, they're maneuvering, trying to predict what those targets is going to be in the future. And then I was saying before, in terms of improvement, we have the ability to refocus some moving targets, okay? And you can see that the target on the left, it looks way more defocused than the one on the right. These are not optical images, so for those who are not really used to looking at radar images, it might be, you know, the same thing, because I don't understand what that is. That's a ship, but for those who are trained to look at this type of targets, the target on the right-hand side is way better than the one on the left. So you can see way more features, you can understand what can be mounted on the deck of the ship and so on and so forth. Of course, you need training for that. There are automatic or aided target recognition systems that can be put in place, and this is effectively a much better input. So this can be done automatically for all the targets that are present in the image and present just the final results. So it's all graphical user interface, and we have delivered this to IMOD, but we have the ability to commercialize this as well to partners that are approved by IMOD. Regarding the Stratospheric Balloon-borne SAR, this is quite an interesting project. It was a bit of a gamble. I think it still is a gamble. This is funded by by NATO. NATO has a program called Science for Peace and Security, which is a paramilitary program, so not really targeting military applications, but more like homeland security, border protection. And what we proposed for this project was a synthetic aperture radar that doesn't go all the way to space, but goes way beyond the airspace. Okay, so a classic mission. You know, we got a launch phase, ascent phase, and then there's a cruise phase where we actually gathering data, forming the images, and sending it down to the Earth. This picture maybe is a little bit better. So just to make you understand, we're going up to the stratosphere in between 20 and 40 kilometers. The balloon is unmanned. It's non-controllable, it just goes with the flow, all right? Goes with the wind. But the interesting thing that the winds all the way up to the stratosphere are very well monitored. So we have mission planning tools that are able to predict exactly, or not, with a certain accuracy, where the trajectory is going to be in the next 2 to 3 hours, which covers usually around 100 to 300 kilometers stretch. What happens is that this balloon eventually keeps on rising because it's a zero pressure balloon, and explodes, and the payload comes down with a parachute, and it's recovered because the payload is quite valuable. I mean, we have also worked to try and minimize the cost production for this payload, so that it may become also expendable for military applications. So you launch a balloon into enemy territory, and then after gathering the data, you destroy it. You don't want any evidence to fall into the hands of the adversary. So it was thought not for military applications, but of course it has military applications that can be interesting for this type of for payload. So the platform is just inflatable balloon. The payload is about a few kilos, less than 10 kilos. So the housekeeping is about same. So we are well under the class of 25 kilos. So there's 15 kilos, sorry. And so there's a category balloon that can be launched that can carry up to 15 kilos that don't require infrastructure at all. So just a car, hook it to your ute and launch it when you're ready. So it's quite an easy system to deploy, it's quickly deployable and easily deployable. Payload, radar system. So basically the payload was developed in Pisa, and the platform developed by the University of New South Wales. What happened is that we never launched it because we arrived at the moment where we were supposed to integrate the system, so come to Australia, integrate the system. It was in the middle of COVID. Australia didn't think about opening the borders, not until not until when it was too late for us. So NATO waited, and eventually said, okay, we've got to close this project because we can't wait any longer. And a few months after they decided to close it, Australia opened the borders. So next year will be at the University of New South Wales to discuss what to do. NATO might potentially open to give us the rest of the money that we needed to do the integration and launch. So hopefully we'll go on with this, and I will, hopefully show you some images in the future, but not for today, unfortunately. We can't do that. So this is, classic sort of homeland security maritime surveillance in the Mediterranean Sea. There's a lot of illegal traffic going from Africa to Europe, from the East Coast into Italy. Patrolling that stretch of sea is quite costly for airborne platforms, for aircraft. Satellites don't have the persistent surveillance that is required, so the reasoning time is too slow, it's too long. So this can be a system that can actually fill that gap. We can have a wide area surveillance with just two ships at the far end and balloons that go east or west-east, depending on the wind. And then you have a recovery procedure to recover the payload. So this is something that is feasible. And again, from a military perspective, you can launch this balloon from friendly territory into enemy territory. When it gets to their height, it's hard to be taken down unless you have a guided missile that costs about at least 100 times more than this system. So it's very asymmetric. And again, you want to destroy the system before it falls into enemy's hands. For that reason, everything has to be low cost, which is. Okay. The platform doesn't cost that much. The payload can keep it a reasonably low cost. And that's one of the possible applications in the military field. So the last thing I want to talk to you about is space situational awareness. Actually, I don't think I have the second topic, the passive radar, but I want to talk to you about the long baseline multi-static radar for SST and GEO. So I'm currently leading a NATO research task group. So this falls within the NATO Sensors and Electronics Technology SET panel. STO within NATO is a very, very nice collaborative platform that we use for many, many things. Space is one of these. As you probably know, sharing data, sharing systems, facilities, information in the space domain when it involves military stuff is almost impossible. NATO provides the means to do that, which is great. And one of the experiments that we put together is it was at the beginning, to me, sounded like a little bit of the idea of a mad person. What we wanted to do is, okay, let's use the powerful radars like the Milestone radar, MIT Lincoln Lab, the TIRA, which is owned by Fraunhofer Institute. They already operate at GEO, so detecting targets at GEO means, okay, with the radar, I'm going to at least 36,000 kilometers. For a radar, it's almost unthinkable of, but you can do it when you have such large apertures, antennas of at least 30 meters diameter, if not more, and a peak power of a few megawatts, which is almost unthinkable of. But the interesting thing is we can do better if we use radio telescopes as receivers. So now radio telescopes are not designed to do this. Okay, they look at this space, and as physicists, you look at constellations and things. And I'm not an expert of radio astronomy, but that's what they do. Radio astronomy is. But we somehow convinced 3 observatories, one in Italy, in Sardinia, one in the Netherlands, Westerbo, and one in the UK, Jodrell Bank Radio Telescope, to actually join us in this adventure. And we started building this system, which is a system of systems, of course. And after a lot of struggle, it took us at least 1.5 years to get the first detection at GEO with these systems. So what we're looking at is improving the sensitivity of the whole system, improving the coverage, and enabling this also bistatic configurations, which could be somehow an advantage in terms of detecting certain types of objects that are deliberately designed to be low observables for monostatic systems. So a lot of interest from the military perspective, a lot of interest from NATO. This is a task group that has been going on for more than 2 years now. It will go on for another 1.5 years roughly before closing, but there's also ideas for future development of this. James Palmer of Salentian Defense is part of this team, but I will not talk about the stuff that he does, probably you already know. Within the space situational awareness, we have done a lot of space object characterization. So one thing is to detect these objects and determine their orbits. The other thing is to understand what they are like, what sort of payload they're carrying, and what characteristic they have, even for disambiguating some of the tracks that you're actually trying to obtain with your systems. Right? So we developed quite a lot of algorithms that are able to characterize these objects, spinning objects, for example, non-spinning objects, objects with rotating parts. We've done a lot of work in this sense. And we have also looked at, this is for the Doppler signature, which is somehow known also as macrodoppler when you have rotating parts within your body. We looked at a number of objects. So collaboration with the joint lab that I'll show you before, the Italian Navy, they have a very nice compact range to emulate far field. And so we did a lot of measurements of objects that we may find in space, and including a 1U CubeSat. Some of the objects that are not here. So we spent quite a lot of time taking measurements. So we studied the Doppler signatures of these objects when they rotate and they move in certain directions and so on and so forth. And also the RCS, so the radar cross-section, to try and understand if certain objects can be visible with a certain radar or not. So a lot of these analyses went to technical report, and we delivered for our MOD. Of course, I can't give you numbers, but it's work that we have been doing for the MOD in the last few years. The last thing is optimize sensor scheduling for space object tracking. And you may be aware there's a lot of objects. You are definitely aware there's a lot of objects that get launched all the time. Some of these objects have to reach the GEO belt, and to do that, they get transferred from LEO to GEO, and in this consecutively sort of increasing orbits, and they have to be monitored continuously. And so there's a number of ways of monitoring this number of sensors that are available. So we did some work trying to optimize the number of sensors and type of sensors to minimize the cost function that is mainly related to the actual economical cost, okay, of the whole thing, but preserving the performance, the requirements that are set for that particular object. Okay, so we did that. This was done in collaboration US. It was project funded through one of the chapters that they have in Europe to fund research projects outside the US. So I'm not going to tell you this. I'm not going to tell you all the details here, but we demonstrated that with a minimum amount of these sensors, so we could optimize with respect to the standard procedure that they actually follow, and still obtain perfectly acceptable performance. All right, so just conclusion. So you fully know this, the attention to space and related business is growing, I would say, exponentially. This is happening in Australia, I can see, but it's definitely happening in Europe, happening in the US. There are strong motivations from both from the civil and military spheres. There's a lot of cross-fertilization that we are experiencing between the two domains, both ways. So we are continuously seeking funding in this area, and just to continue to produce these high-level scientific and technological results. We hope that one day we'll be putting one of our payloads in one of these satellites that will be orbiting in the future. For the moment, we haven't been able to do it. Hopefully, we'll soon launch our first stratospheric balloon, and then we'll hope to go up to space. So, opportunities. There are opportunities, funding schemes that can be explored for international collaboration with Australia. One of these is surely NATO, and this is already happening. That's one way to do collaboration. Across is more like a non-funded scientifically collaboration, but if we want to go through some more serious level of funding, there are opportunities. One of these, as I was mentioning before, is government-to-government collaboration, because at least in the military world, but not just that. Of course, there may be ways of creating opportunities for collaboration across that would involve my lab from our side and any industry or academic partner from the Australian side. So I'm happy to talk about this. Now, if we have some quick reaction, or in the future via email, via online, so I won't be here for very long. But anyway, thanks again to Nicola for this opportunity. I hope you enjoyed the seminar, and I'm open to questions. And the slides, I can make them available, Nicola, to you. And if you want to then put it online, this is all distributable.
Thank you, Marco. Thank
Pleasure.
you. I think that everybody's appreciating your presentation.
Thank you.
Just I would like to start to say that we are seeking the funding too. So if we are into,
We're on the same boat.
But the innovation cycle is very interesting. Probably the Smart SAR CRC is something like bigger than your model. So we have 20 university in our consortium, and then we have in total 130 stakeholders. That is include startups and also company like BAE, like Airbus, Leonardo in terms of Igeos is involved too, etc. So this model is quite interesting in terms of you have all the stakeholders involved. And I really would like to explore with you a sort of collaboration that starts from the bottom, so something like bottom up. So start with small thing, and then we can think about bigger one. You are 22 of experience, and the 22 years you are here. When I met you, I was late in 2007, 2008. You're still working with the DAG, University of Adelaide. You work with University of South Australia. You work with the STG. All of these three organizations are core partners of Smart SAR CRC. So it will be very easy, to find some common elements, and that is mainly, driven by you. We have something very easy to start, like a joint PhD, completely funded by us, including also the fee at the university. And also we have a new activity, a new program, the visiting scheme, visitor research scheme. So in other words, give people like you for 1 month to spend with us and stay with university that you are identified, that for us is quite strategic, to stay with us for 1 month. So there are something that just to start, but of course we are more than happy to work together with some project. For example, we have some project with the European Space Agency, and that is important, the formula. They fund the money for their activity, we fund the money for our activity, but we are together in some program. So it's something like also European Union, you are not able to pay us, and of course we are not able to pay, the European organization, but everyone can pay by themselves and work together. So that is a model that I would like to explore with you in the future. But say that, I would like to open, Peter, would you like to say something?
Put me on the spot, Nicola. Yeah, I think the NATO links are interesting. I mean, I know the NATO S&T organisation very well, and I think they do challenge or pursue really challenging research problems. And the fact you're already connected in with a number of academic universities is interesting. So I've got a number of questions and comments, but I'll probably follow up offline, Marco. I think there's a lot of work you're doing, which is absolutely relevant to us. The radar processing piece is interesting. The distributed baseline piece is interesting. The stratospheric platform piece is interesting. So, I think there's a lot of things we're doing where there's a lot of scope for further collaboration.
Thank you. Thanks.
Peter, of course, is one of us. SMARSAT CRC is the director for defense activity inside the SMARSAT.
Right. Mm-hmm.
Any other questions around? No? So I think that we just say thank you very much to stay with us, and hope that we can generate some bilateral collaboration. Thank you, Marco.
Thank you. Thanks, Nicola.